I'll say a few words about artificial intelligence and mobility, with a particular emphasis on safety and security. Few brief words about DFKI, the German Research Center for Artificial Intelligence. We're a sort of medium-sized research institution with sites in Kaiserslautern, Saarbrücken, and Bremen, where I'm from, also sites in Berlin. We're about 650 full-time employees. So we are, I think, the largest research center in the world, which is purely dedicated to artificial intelligence. And we cover all aspects of applied artificial intelligence. So this is image and speech processing, human-computer interaction, machine learning, deep learning, robotics, and what we do, our department in Bremen, is formal proofs for safety and security. We cover all sorts of advanced software technologies. What I'm going to talk about now is artificial intelligence and mobility. And if you look at modern cars such as these, they already have a number of capabilities which make them nearly autonomous. I mean, modern cars have quite a number of microprocessors in them, and essentially they're sort of networks on wheels. You can buy these cars, they're already on the market, and they have, as I said, a lot of advanced assistance options which make them nearly autonomous. There is, of course, the Google car, which is truly autonomous. So we're not far off from really intelligent cars like this one from science fiction, which does things on its own. But this comes at a price. Just while preparing this talk yesterday evening, I found an article in the Guardian, which says, and I quote, "Tesla driver found asleep at the wheel of a self-driving car at 150 miles an hour, or kilometers an hour." So this is in Canada. It says that police in Canada have charged a man with speeding and dangerous driving after he was found asleep at the wheel of a self-driving car as it traveled at 150 kilometers an hour down a highway in the province of Alberta. So you see, these cars are there. They are essentially self-driving, even though we're not allowed to call them that, but they cause problems. And one problem, this is a very famous incident. This was roughly 2 years ago, an autonomous car. This was a test car from Uber, essentially, collided with a pedestrian, causing fatal injuries for the pedestrian. And of course, with an incident like this, there was a huge investigation. There was a report by the National Transport and Safety, the US body which investigates traffic incidents like that. And it was found that the pedestrian was detected by the sensors, but the car didn't brake. And also the driver, which was sitting inside the monitor, was supposed to monitor it, didn't intervene. So the question is, how could that happen? We look at this in depth a bit more later, but the question is, how could that happen? And how can we make sure it doesn't happen again in future if we have truly intelligent cars? And my thesis here is that safety is essentially the prime obstacle, the showstopper if you want, for the widespread adoption of autonomous driving. Or put it the other way around, if we can't make autonomous cars safe, they will never be accepted by the market. So the question is, how can we make them safe? How can we make more general, how can we make artificial intelligence applications safe? And that's what I'm going to cover in this talk. So we need to talk about, firstly, how does artificial intelligence work at a very general level? Anyway, how do computers work? How does safety work? How do we ensure safety at the moment? We have planes which are more or less controlled by computers, and they don't, some recent things with notwithstanding, the Boeing 737 MAX incidents notwithstanding, planes are generally fairly safe. So how does that work? And from that, combining these two, what is the problem and how can we solve it? So let's go through this in a bit more detail. How does AI work in general? In general, programs are essentially just computations. If you look at collision avoidance of an autonomous car, for example, if you program it, Essentially, if you have an autonomous car like that, you have distance sensors which measure the distance to an obstacle. And so this is just the simplest case, it's just a number, so 50 meters to an obstacle. And then you can compute for a car, you can, from the current velocity, you can compute the distance that it needs to travel before it comes to standstill. And then you have, while driving, you can say, well, if the distance becomes, I need to come to a standstill, becomes larger than the distance to an obstacle, before that happens, I should start to brake. So that's a very simple program. And essentially all programs are like this. They are just computations involving integers and case distinctions and loops. So you compute things with integers, you compare them, and then you loop around, you jump around. And this is what we call computable functions. And the notion is called Turing computability. And these are normal programs. These are sort of normal programs that we use, that we write without involving artificial intelligence techniques. They work different. They work by presenting lots of examples and then kind of making the program behave such that the examples are treated correctly. So more precisely, you have a training phase where you present the program with lots of inputs labeled with a desired output. So if this is an example here, if you want a program to recognize traffic signs, in particular these signs, which is a priority sign, if you want to recognize these images, you give it lots of images of traffic signs, and you say, well, this is the one which I want you to recognize, and this is the one which I don't want you to recognize. All right, so you give it a label here. Say this is okay, this is not okay, this is not okay. It's a different sign. This is okay, that's a correct sign. This is not okay. This is not okay. This is okay because it's a correct sign. It's not okay. It's a stop sign. This is not okay, even though it's yellow, but it's the wrong shape of yellow. Right, it's a square, it's not a rhombus. This is obviously wrong. This is a correct one, and this is wrong again. And then once you've done this a lot of times, and obviously 12 traffic signs are not a lot, you do this with a couple of hundreds of thousands of pictures, then you come into an operational phase where you just give it an input, and then you see what output the program is associating with it. So you give it an image like that, and then you ask, now what's your output? And then hopefully the program says, this is not a priority sign, this is not a priority sign, this is a priority sign, that's not even a traffic sign. And this one, now, it might say no, it might say yes, depends a bit. I mean, this looks like a priority sign, but there are these crosses here. So essentially, it shouldn't recognize this, but you need to train it to not recognize this, because this is the end of the priority, and it shouldn't say this is a priority sign. But it only does that if you give it images like that during the training phase and say it's wrong. So how does this work? Well, these nets use artificial neurons. So these are essentially nodes connected to other nodes, lots of other nodes, and the input is weighted, and these weights are what makes these things work. Essentially, a single neuron is connected to various other neurons. The input is weighted, and then you have an activation function, which here is called phi, which takes all the inputs here and produces an output. And then the output can again become input for other neurons. And this is then what gives you these layers. So these nets have an input layer, which, for example, if you talk about pictures, it's the single pixels of the picture. And then the input is mapped to various hidden layers of neurons. And then there is, at the end, there is an output. And the output layer can be fairly small. If you just want to recognize whether something is, for example, a traffic sign or not, it could just be, it could be just a single neuron, it could be a number of neurons which encode the output that you want to have. And crucially, these weights here, they change during the training phase. They start off with some initial value, and then they change during the training phase when you give this net hundreds of thousands of inputs together with the associated output, and then the weights are changed such that the input is actually maps to the correct output, right? And then if you give it some more input, which is more or less like the input that you've given to the net. It hopefully produces output which also fits the output that you want to have. So that's completely different way of operating, obviously. And these two ways of programming are called symbolic and sub-symbolic. You know, these traditional programs are symbolic. We call them symbolic because they represent the world in the data structures and the decisions that you take in the source code, right? So these, you can picture these as either source code, or you can, at a higher level, you can picture it as diagrams like this, where you sort of, you do something and then you take a decision based on, for example, particular input data. These AI techniques, such as deep learning, they are statistical methods. You give a lot of inputs, and then statistically comes to an output, and the decisions that it takes are represented somewhere in the weights of the artificial neural net. So the decisions are spread across all these weights, and there are quite a number of them, and that's why they're called sub-symbolic. And that means that these sub-symbolic programs, deep learning, they are not more powerful. They can't do anything more than you could do with normal programs. They're different. Sometimes they work faster. Sometimes they're easier to construct because you just give it lots of training data. And if you have the labeled training data anyway, then you just need to train the net, and it can does that on its own. You don't need someone to painstakingly construct the program, but they are not entirely predictable. If you give it data outside the training data, it's never totally clear what might happen. But they are, as I said, they can't do anything more. They're Turing equivalent. They're just about as powerful as normal programs. What does this mean for safety and security? And for that, we need to briefly look at safety and security. How is it done traditionally? Firstly, what is safety? And I'm going to talk a bit more about safety here because that's where I'm coming from. Security is essentially more or less analogous to what I'm saying here. Safety, the absolute definition of safety is that it's the complete freedom from accidents and losses, as taken from this book by Nancy Leveson. Of course, there is no such thing as absolute safety. You can never be sure, in particular real-world system, always things might happen which you haven't covered. So the technical definition that is used in the relevant norms and so on is that safety is the freedom from unacceptable risks. So if you're talking about safety, there was always this risk analysis involved. So you try to analyze the risk, you try to quantify the risk, and then you say, well, there was a certain risk of something happening, but we want this risk to be, if it's below this number, then it's acceptable, and everything else is unacceptable, and we don't want that. And then obviously, the more critical something is in terms of what would happen if it doesn't work. What would an accident mean? Would there be a risk to the safety of people? You know, would there be a risk of bodily harm, of seriously bodily harm of one person or many persons? Then the safety requirements become more stringent, and that's. These situations are covered legally. I mean, there's a legal basis here. There are laws which govern how things can be run. There are laws governing, for example, how you can run cars. You know? And if you want to build a car, then it needs to have it's strictly regulated. There is, for example, in Europe, there is the machine directive in the European Union, which prescribes how all sort of machinery can operate. These laws operate on a fairly abstract level, and the technical way of implementing these are encoded in norms and standards, which are typically more geared towards a specific application area. So for example, there was one called the 26262, which concerns itself with safety of automobiles, of cars. There is one which is called 50821, which is concerned with safety of trains. There was an originally American norm, which is called the DO178B, or C is a new one, which is concerned with software of planes. There is one, where are we? There is one which is called the 61508, which is concerned with all kinds of electrical appliances, be it robots or be it household toasters. And there is one, which I can't see at the moment. There is one which is called the common criteria, which is concerned with security. So these norms then make fairly concrete suggestions and prescriptions what you have to do to make a system safe. And they work by regulating the process of software and system development. And the idea is twofold. Firstly, is the assumption that if the process is well regulated, then the output will be good as well, good in the sense of safe. But also it means that if the development is well regulated and well documented, you can always trace decisions back, and if something happens, you can always you can apportion blame, and you can make sure why something has happened the way it did. And that's very important for legal reasons, obviously, because the legal question is always, when something goes wrong, who has to pay for it, essentially, in the end. And that's covered by, that's this reconstructability. You can always reconstruct the development process. You can tell whether something has gone wrong, why it's gone wrong. And then essentially you can say this has gone wrong because there was a combination of circumstances which nobody could foresee. Or there is, you can say this has gone wrong because people have been sloppy, because there have been essentially cost cutting. People didn't do things very, very carefully because they wanted to be fast and quick. And then, of course, that would have legal implications. This process regulation means that typical development produces lots and lots of documents. That's not ideal. It's actually better to verify the functionality, not regulate the process, but verify the functionality. And when you do that, you get this as a sort of side effect, because if you verify something, it also means that you can reconstruct how things happen. There's something called functional safety, right? Functional safety means that you make sure that your system behaves as it should, and that this behavior then is safe. And you do that concerning software. You can do this both on the hardware and software level, and particularly the interplay of the two, using systematic tests and formal proofs. So how does that work? Here's a famous example from the literature. It's a railway crossing. Assume you have a railway crossing like that one here on the left. So in reality, this thing looks like this, right? It's a road and there's a train crossing. And the first step to make sure that this is safe, whatever that means, is you have to build some kind of abstraction, because then you can state the safety property. You can say, what do I mean by safe? What does it mean? Safe means here that the car is not overrun by the train, but what does it mean more precisely? First, you construct a model. So the model should cover all the salient aspects of reality. So essentially here, the relevant aspects are that you have the train tracks here, you have the train traveling, you have the street with a car, the car travels, and you can, for example, you can simplify with a simple model. You can simplify the car only travels down the road, and the train always goes from left to right. Doesn't matter. It should go in two ways. And there is the gates, the gates of the train crossing. And the gates can be open and crossed. And now, of course, the important thing is that the car can only cross if the gate is open, and the train, when the train crosses, the gates should be closed. And you can formalize this by something which we call finite state machine. Essentially, you have the various components of your system all have their own states. So the car has the states that it's away, and then it come here, so it can move between the states as the arrows indicate. So it can, from away, it can approach, and then if the gate is open, it can cross, and then if the gate isn't closed, so the gate is still open, it can leave, and then once it has left, it's away, and then maybe it can come again. And of course, it should be another car, but again, is some sort of is an abstraction that we make. On the other hand, the train has the same sort of behavior. It's away, it's approaching, but it can only enter the crossing if the gate is closed, right? And then it crosses, and then it leaves, and then it goes away. And the gates, they can be open and closed. You know, they can go up and down, and they are open usually. And then when a train is approaching, they become closed. And until the train is leaving, right? While the train is not leaving, the gates should remain closed. Then if the train is leaving, then it goes again, the state changes again, the gates open again, and then the gate is open until the train approaches, right? So the gate changes its state when the train is approaching. And you might think this is safe. What does safety mean now? The safety property is that the car and the train are never on the crossing at the same time, because that would obviously mean that they collide. That's all we don't want. And we can write this down formally. So the idea is that with a model like this, you can formalize safety properties in formal logic, something called here linear temporal logic. And you can say, what does it mean on the crossing at the same time? Well, it means that the state of the car is crossing and the state of the train here is crossing, and we don't want that. So we want not car equals crossing and train equals crossing, and we want this for all times, and that is the G here. So we want the G stands for globally. At all times we do not want that the car is crossing and the train is crossing. You can write that down in formal logic, and then there are tools which actually take a description of the system in terms of formal finite state machines like that, and safety properties like that, and then they verify that the safety property either holds or doesn't hold. The nice thing about these tools is that they actually find counterexamples, so they can tell you if the safety property doesn't hold, it can tell you exactly the situations that and how they develop in which it doesn't hold. And in this instance here, well, maybe as an exercise, you can try to figure out whether it's safe or not. It actually isn't safe, as a spoiler. So you can find that sort of things out. As far as software goes, you can even be more precise. You can reason about the software as it is. You can reason about the source code as it is without constructing a model of the system. You can directly reason about the source code, because software is something symbolic, right? And that's where this word comes in again. The computer executes the software in a very predetermined manner, and you can make use of that to reason about its behavior. So you, again, just like the train, you write down the properties that you want the program to exhibit in some kind of formal language. So for example, here's a sorting algorithm. This takes an array of integers and of a certain length here, and then it should sort this array into order. So you write this down as a sort of precondition that says that this array has a certain, this A is an array of a certain length, len, and then you say as a postcondition, well, afterwards I want the array to be sorted, and I want the array afterwards, A, to be a permutation of the array as it was before. You can use that, and you can use the program. So here is a C program which does that, which implements this algorithm, and you can prove that it satisfies this obligation essentially by simply executing the program. You sort of go through the program, and you find out that it satisfies these properties. You generate so-called proof obligations, which you can then automatically prove. And for simple programs like the sorting program, that works on its own. For more complicated programs, you need to, these annotations need to become a bit larger. You need to annotate while loops, but just remains, you can do this on the level of the source code. You can reason about behavior of the source code. You can prove that it satisfies certain properties. Right? So that is how we do safety. And this is how you prove the safety, for example, of an airplane, or as it at the moment. Right? So there is this whole corpus of work which works by abstracting from the real world into a formal model. And then you can prove on the level of the formal model, you can prove properties which reflect on the behavior of the system in the real world. And essentially by that, you can make sure that the system in the real world exhibits the desired behavior. And this has a lot of advantages. It's unambiguous. It's sort of complete and consistent, and it's checkable by machine. So these proofs that you do here, you can run them through a machine. They can be very large and very longish, but because you can check them by machine, you can be fairly sure that they are indeed correct. What's the problem with AI in this setting? Well, the problem with AI is that the functionality of deep learning and related techniques is encoded in the weights of the net, and that's not something you can reason about easily. So the output for the input beyond the training data can be unpredictable. There is this example here where you've trained a net, for example, to recognize handwritten numbers, or here to recognize traffic signs. These are the training data here, and then you give it slightly different data and produces wildly varying results, even though the changes are very small. I mean, here for the traffic signs, they are hardly recognizable, right? And so this sort of thing happens quite a lot with deep learning techniques. There was another example here, which I found in the net. There was the source. This is a deep learning network which recognizes persons, and you can see that it recognizes this person here on the left, recognizes him very consistently, but the one on the left, he easily fools the net by having this picture, holding it in front of him. If he passes the picture to the person on the left, then suddenly he isn't recognized anymore. So the deep learning net here is easily fooled by this picture, people holding this picture in front of them. And of course, this is something that you can't really predict from the net. And this is, from a safety point of view, this is deeply troubling. I mean, sort of, if you have an autonomous car which detects pedestrians and by deep learning, and doesn't detect them if they hold something in front of them, for example, brightly colored shopping bag, then it would run them over. I mean, that's something that you don't want. And you want to guarantee that your network doesn't do that. So the functionality of learning algorithms is not reconstructable and not really verifiable. There was a whole field of AI which deals with that. It's called explainable AI. You can, for image classification, you can look at the weights of the nets and sort of trace them back to the pixels of the image and say which pixel of the image give you the classification. And the famous example here is that this network which classifies huskies versus wolves. And it turns out that it was given lots of pictures of huskies and wolves. And it turns out that for the classification, it didn't make use much of the actual animals, but the background, because the huskies were always, pictures were always taken in snowy conditions. So it's kind of, you can see this here on the right. It recognizes when there's lots of snow in the background that it should be a husky and not a wolf. And that's obviously not something that you want. And here you can actually, with these techniques, you can have a degree of explanation, but still not enough to actually guarantee functionality. So what should we do? The idea is, if you have a system which has a behavior governed by, for example, neural nets, you should always have some sort of formal model like this one, where you can prove that the system behaves safe, and then use that to make the system safe, to restrict the possible behavior of the deep learning or AI system. What do I mean by that? This is a project that we've done in Bremen a couple of years ago. So here we have something, autonomous robot, a small robot like that. This is just a demonstrator vehicle. What you can do for a robot like that, it goes back to the example at the beginning. You can compute the area it covers while braking at the current velocity and angle, right? So if it travels slowly ahead, it covers the green area here. What is happening? Sorry. I seem to go back. Sorry, I lost control there of the system for a second. So, as I was saying, if it goes slowly ahead, it covers the screen area. If it goes around the corner like that, it covers the screen area bent into a corner. And that's all fine, but if it goes too fast ahead, it runs into an obstacle here in this situation. So you can compute this, what we call safety zone. You can use a LiDAR sensor here, this red thing, to detect obstacles, and then you can very easily see if there is an obstacle in the safety zone, and if it is, then you can initiate braking. So we've implemented this in C, and we verified it formally using techniques that I described, and you can use that, for example, to make self-driving vehicles safe. And the idea is that this is just a safety layer. This doesn't say anything about how the vehicle is driving. It could have a layer above, on top of that, which actively avoids obstacles. And you don't need to formally verify that layer, because you know that always there is always the safety layer, which guarantees you that it comes to a standstill if you try to run into an obstacle. So that is the safety layer, which computes the safety zone and brakes if it's got to, before it runs into an obstacle. That would be the box, the red box in the previous slide. Okay, we come to a close. What does that mean? Let's go back to this incident that I described with the Uber car in Arizona. The accident report constructed the chronology here, and it turns out that the car actually detected the obstacle fairly early, 5 seconds before the collision with the radar and LiDAR sensors, but it didn't initiate braking because it changed the classification of the obstacle. It couldn't really decide or stick to a classification whether this was an obstacle on the side of the road, or whether this was an obstacle crossing the road, or whether it was a car driving along the road. And it changed the classification. The core problem was that whenever the classification changed, the movement of the object wasn't traced. So it didn't recognize that it was on a course across the road, which leads to a collision. And that's just because that was just because the safety architecture here wasn't very good. There wasn't much of these sort of formal methods that I've described, right? And then and also the monitor driver, you can't really blame him too much, I think, because there is a video here which shows the crash from the driver's perspective. Essentially, it was very dark, and he was only he could only spot this obstacle essentially a second before the crash, and so essentially he had to sit in the car, which drove all by itself, looking very alert through the dark night, and be ready to start braking. So again, here the problem was that the system architecture wasn't built according to established principles. So this was something that could have been avoided using the established technologies that we have in this area of safety engineering. So what does it mean? It means we need explicit informal system modeling. We have these technologies of formal methods and formal verification and so on to make systems safe. Artificial intelligence is useful, very useful for specific tasks, such as image recognition, for example, but it shouldn't be used for end-to-end control. I mean, there should always be a symbolic layer somewhere in the system which is responsible for the safety of the system. And that also means we can make autonomous cars and similar safe, but it may not be cheap. I mean, it has to be said that developing software in this formal manner is fairly expensive. And there is this tendency to use deep learning techniques for cost cutting, because as I said, it's fairly, once you have the labeled training data, it's very easy to actually train the net. You just need to run it for a couple of days and then you have a trained net. But as I said, this is something that you shouldn't use for overall end-to-end control of the system. Okay, conclusions. As I said, I think that for autonomous car safety can be something of a showstopper. We need to tackle this. And we have a lot of methods at our disposal for symbolic systems which are well understood and well used. And the sub-symbolic techniques, such as machine learning, deep learning, and so on, can't really be handled very well by these methods. There's a lot of research going on there. But how to combine these techniques to make systems safe is, at the moment, the subject of a lot of research. But I think by combining these methods along the lines that I described, we can make cars safe, and we can make autonomous cars be widely accepted in the marketplace. And with that, I come to a close. And thank you for your attention, and I'm open to any kinds of questions.